And share my screen, don't want to forget that again. And so, yeah, welcome everybody to our big data class today. Last time we were talking about, so we started talking about these strategies that the query planner uses to actually implement our queries. So here are 3 strategies that we've seen so far in particular. And these are fall into this category of table scanning strategies. These table scanning strategies are sort of for the simplest possible queries where we're just selecting some columns from just a single table and where there's some condition. And so today we'll start adding some more complicated clauses to these queries, and we will finish up this short table scanning strategy session with one last method. We will, there's this PDF file with this integrated questions. We'll start probably getting to this today as well. Any questions before we get started? Okay, so yeah, last time we saw the sequential scan. Main idea is that it can always be used. It's just a for loop over the data, and so linear runtime and everything. Then we saw the index only scan and the index scan. The main idea of these 2 methods take advantage of the index to convert that linear runtime down to logarithmic runtime. And the actual runtimes here have fairly complicated formulas, or relatively complicated formulas. But the key idea is that we're logarithmic and in, so going to be significantly faster. And then the difference between the index only scan and the index scan is the index only scan, the only thing, all the information that we're accessing is somehow contained in the index. Key vocab term is that makes the index a covering index. And so we don't need to access the table pages at all and only access the index, whereas the index scan, we're actually accessing the tables as well to get additional information not in the index. This time we're going to start talking, or we'll finish also talking about a bitmap scan. And that's sort of an extension of this index scan to an even more complicated situation. I'm going to switch over to the terminal over here, and I want us to, again, I'm in the Twitter Postgres parallel in my solution here as the setup that I'm in. And so this is we'll have a relatively big table that we're working with and experimenting with these different indexes and scanning strategies. And what I want us to start with actually is, so we'll be going into pSQL. Actually, yeah, we're going to go into bash first and then go into pSQL. And pSQL -- user equals Postgres, like that. And we had this tweets table. This is the table that we're working with. And we're going to be creating a bunch of indexes on this again, like we did last time, and seeing how it affects our different table scan methods and the runtimes of doing different operations. The one thing that we didn't do last time, though, which I want us to start with this time, is actually calculating how many pages are in this table, because that will be useful for us to compare with the some of the information that we'll see later. So we've seen how to do that before, but just a quick reminder. So there's this PG_class table, and in PG_class, there's this OID from PG_class where rel name equals tweets, like this. And this OID tells us the name of the file that actually stores this table. And there's also a PG_database, and the database lists all the databases. Recall that in Postgres, a database cluster is a collection of these individual databases on a single machine, so nothing parallel about it. And I need the OID of our database as well. from PG underscore database. This is our database. This is the OID, so 1345 and 17405. I'm going to get out of pSQL here and recall that, so PG data, this environment variable contains the information for Postgres. It's where it stores all its information. And then in the base folder, we have all of our databases. This is the database that we want to look in. And then that has all of our tables. This is the table that we want to look in here, like that. Base 13445. And then 17405, 17405. Where did that go? Equals tweets. Oh, that's embarrassing. This was working. I thought I just did this like 10 minutes ago. Open up pSQL again. Postgres 13445. PG class 17405. Well, let's try. I'm going to do the find command lists all of our folders in PG data, and then let's grep 17405, looking for that particular table. Why did that do that? It's not there. I don't know what I did. I'm sorry. But this, did I accidentally delete this tables from tweets? Oh, there's a bunch of stuff here. So I'm sorry about that. I'm not sure why I'm not able to find this table right now, but the table itself was occupying 39 megabytes of disk space. And if we did the 39 megabytes divided by 8 kilobytes per page, then we got, I don't even remember the exact number now, but we'll calculate it. Python 3, so 39, 1, 2, 3 divided by 8. Actually, 39 times 1024 divided by 8. 4992 is the number of pages in our table. So number of pages equals 4992. The way I calculated that was this was the size. This is the size of the table. I'm not sure why I couldn't find it. And then in kilobytes, 8 kilobytes per page. So this is the number of pages in the table. And we're going to be seeing some things here where it's, as we're running our queries, it's going to tell us how many pages it's actually looking at. And so by comparing that to this number here, we'll get an estimate of like what percent of the data, how much of the table it's actually having to look at as it's running the different scans. So yeah, takeaway so far, tweets table has this many pages in the heap itself. Any questions about that? Okay, so in the tweets table, if we wanted to do something like selected tweets from tweets where lang equals in, so all the English tweets, get all the English tweets like this, and that would list the tweets right here. We can put the explain command in front to see what the query plan for this particular query is. When you use just the explain by itself, explain calculates the query plan, but doesn't run the query. What we're going to see next is there's this explain analyze command. Sometimes analyze is put inside of parentheses. Sometimes it's not. Doesn't have to be. It's optional. And this actually runs the query, and so it tells us like how much time and resources it actually used, and tells us how many actual resources used. So here, rerunning this command, there's the explain version, and then explain, analyze like this. It's a little bit longer of information. You can see that it's actually bleeding over the edge of the screen right here. And so that's why I opened up the pager environment. But the main new pieces of information are down here, this planning time. Planning time is the amount of time it took Postgres to compute the query plan that it's going to use. So that's like the runtime of just the explain. And then the execution time is how long it took to actually run the query. So 45 milliseconds. In general, the execution time almost always much, much larger than the planning time. Over here, there's this new piece of information not included in the explain. This information over here was included. This information only included in explain analyze. This information over here represents the estimated runtime of our query, and this is of this particular step of the query. And this is the actual runtime of that particular step of the query. The way to read this is when it says cost over here with these two numbers. This first number here is what's called the startup time, so the amount of time it takes to begin this particular node over here. A sequential scan, there's nothing to do to initialize it. It's just a for loop. You just start it instantly. So it'll always have a 0 over here for a sequential scan. As we see more of these techniques, we'll see that some of those techniques have a larger startup cost, and that'll be a trade-off that we'll have to, or that Postgres will be trading off for us. And then the second time over here is the amount of time that Postgres thinks this algorithm is going to take. The units for both of these two things are unitless. So it's tempting to think of it as like maybe milliseconds or something like that, but that's not the case. It's just bigger numbers are slower, smaller numbers are faster, and there's no actual units associated with these numbers. On the right-hand side, in the actual time, these have the same meaning of the startup cost and the total runtime, and the units over here are in milliseconds. So that's why these numbers are very different than these numbers. But in general, you should see that like large numbers over here correspond to large numbers over here, and small numbers correspond to small numbers. The rows over here, this is the total number of estimated rows that Postgres thinks this algorithm is going to return. And so here you can see this is a pretty accurate estimate that Postgres thought that it was going to get just over 40,000, and it did in fact get just over 40,000 rows. And so this estimate right here is how Postgres is one of the things it uses to determine which of these query algorithms to run. Let's see, in this particular case, we don't have any indexes yet, so the only algorithm we have available is this sequential scan. So let's go ahead and create an index. So create index on tweets, and then we're interested in the lang column over here. Anytime we have a select statement, in order to make it faster with an index, the index must be on one of the conditions over here in the where clause. And so let's put lang like this. In this case, this index has the language over here, but this query uses more fields than are contained in this index. It uses just the lang. The index has only the lang field, only lang. And so this here is not contained in the index. And so we must not use the index only scan. We could use an index scan or a bitmap index scan. And let's go ahead. I'm going to take away the analyze and just explain this, and we'll see what we get as our algorithm here. So explain that, and here you can see that we get bitmap index scan. So this is that fourth type of table scan that we haven't talked about yet. We'll talk about this one next. And so yeah, the bitmap index scan, what's being used. If we were to change this say away from English to language equals AM. This is what we saw last time, Amharic. Amharic has only 2 different tweets written in Amharic, and that uses the index scan. English has the 40,000, and so that will use the bitmap index scan. And now that we've just seen like physically what that looks like in these query plans, we'll explain why we would want to use the bitmap scan in this case and the index scan down in this case. Before I do that though, any questions about reading these query plans?
Does it have like, because it's able to estimate the number of rows, it's going to return back. How does it do that? Does it have some like, internal knowledge of like how many observations?
Yeah, the question is how is Postgres able to estimate the total number of rows that a particular query was going to return? And internally, there's what are called statistics in the PG underscore, not sure the name of the table. There's a statistics table that just stores some basic summary statistics of all of the tables in your database, and Postgres uses that to guess how many results you're going to get from a particular query. One of the things that we're going to see is important is that the reason Postgres is choosing to use this index scan right here is because it's guessing that there's going to be a very small number of rows returned, whereas up here it's choosing to use the bitmap index scan because it's guessing that there's a very large number of rows returned. And so the fact that Postgres is able to make these guesses is really, really important, and the accuracy of these guesses has a huge impact on our runtime. In order to update the statistics that Postgres maintains about each of these tables, the command is analyze. You say analyze, and then the name of the table like this, analyze tweets. And it goes through and recalculates those statistics that it's going to use to determine which algorithm to use, basically guessing how many rows each of these is going to create. And so after doing a large insert into a database, it's really important to run this analyze tweets to update these estimates so that you'll get the good estimates here and get the good corresponding algorithms over here. Okay, so given that we have these estimates, that there's a small number of rows here and a large number of rows here, that's what's causing the large number of rows causes the bitmap index scan, and the small number of rows causes the regular index scan. And so why is that the case? We talked about last time that in the regular index scan, what we're going to be doing is we're getting the tuples back one at a time from all of the pages. So here's some pictures that we drew last time, that if this is our B tree, that in the leaves of the B tree, so technically a B plus tree, because in the leaves of the tree, we're storing the tuple IDs. And as we do our scan, we're getting back the tuple IDs. And instantly, as soon as we hit one of these tuple IDs in an index scan, we're going to instantly look it up in the heap table. In the case of the Amharic query, there's only 16 rows. So at max, we can look up 16 different heap blocks. But in the case of the English query, we're going to have about 40,000 different rows. And so if we look up each tuple ID individually, we're going to look up 40,000 different tuple IDs. That's 40,000 different blocks that we're going to load from the heap table. And that's significantly more than the total number of blocks in the heap table. We saw before that the number of blocks in the tweets heap table was equal to 4992. And so this number here, much, much smaller than this number here. And so if we had to read this many block pages doing an index scan, that would be super, super inefficient. It would be better just to do a sequential scan over the entire table, reading each block once. So the way the bitmap index scan is different than an index scan is the bitmap index scan we'll first scan the entire index, generate a list of all possible TIDs, sort the TIDs according to their physical location on disk. And so originally these TIDs, we're getting them in sorted order according to how they're stored in the index, but how they're stored in the index has no relation to how they're physically stored on the disk. That it's just, yeah, these TIDs can be in any arbitrary order. But because we're doing this sorting the TIDs according to their physical location on the disk, then we only have to visit each block at most once. Everything that I've listed right here, these steps, that corresponds to this specific bitmap index scan step. So all of that is the bitmap index scan. And then the bitmap heap scan right here is go through the list of TIDs, sorted TIDs, accessing, put it on the line, accessing each heap page at most once. And we know that we can guarantee that we'll access it at most once, because after we stop seeing tuple IDs from a particular page, we're never going to see those again. So when we look at the asymptotics of a bitmap heap scan, the total number of pages accessed for both the index scan and the bitmap heap scan is going to be O of k for both of them. K again being the total number of results that we get back. But up here, this is really more of like a theta k. We're going to access each page exactly once for each tuple ID that we get back. Down here, we're guaranteed to access the minimum number of pages, never accessing the same page twice. And so this is typically going to be much, much smaller than an index scan. This really is an upper bound, a big O. And this up here really is a strict upper bound, more of a theta than a big O. So the bitmap scan is going to be more efficient when when k is relatively large, and so we're strong chance of accessing the same page many, many times. Again, that's why on these queries right here, Amharic, very few pages being accessed, uses the index scan. English, many, many rows being accessed, many, many pages being accessed, uses the bitmap index scan. And for both of these two scan types, again, all of the information in the query does not have to be contained in the index. And in particular, these index scan types are going to be used when there's something in your select column that is not contained in the index. If we were to change our, let's see, I'll pause here for questions before changing the index. Are there questions about the bitmap scan? Okay. Maybe, yeah, one thing I'll say is that the way this is going to be important for you grade-wise in this class is that on these sorts of questions over here, one of the types of things these questions are going to be asking is, like, if we're trying to use a bitmap scan, make sure that you create a certain type of index. Or if we're trying to use an index scan, make sure that you try to use a certain type of index. So we'll get to that in a little bit, but that's grade-wise how this concept's going to impact you. So the for both of these scan types here, if we were to recreate our index, so Control R, create index using the multi-column index. So again, a multi-column index will have two fields down here or multiple fields down here. And then it tweets like this. Now, both of these queries can be done with an index-only scan because all of this information is contained directly in the index. And an index-only scan is not going to access the heap at all, and so there's index-only scan always better than just an index scan or a bitmap index scan. Remember, if I do \D and then the name of the table, that'll give us all of the indexes that have been created for the table. So down here, we have created this, this index right here. And so now we have available for us the possibility of doing an index-only scan. The query planner is choosing for some reason right now not to use an index-only scan. It's choosing to use a bitmap index scan. We can force the query planner to use, well, let's see. So in Postgres, you can't force the query planner to use a particular algorithm, but you can force it to not use a particular algorithm. And in order to force it to not use an algorithm, you say set and then enable the name of the algorithm. So enable bitmap scan equals off will disable the ability for it to use a bitmap scan. And so now if we rerun this, it's saying that it's using the sequential scan. I think I probably enable index only scan equals on. Okay, where language equals you are choosing not to use an index only scan for some reason. There we go. It was choosing not to use an index only scan because the table had not been vacuumed. We'll see in a little bit about how vacuuming affects all of our index scans. But there we go, index only scan. And that'll also work with Americ index only scan. And we can use the index only scan again because this index right here contains all the information we need. We can use this index for an index only scan. We cannot use this index for an index only scan. Any questions about the index only scan versus or any of the four index table scan types methods?
Just hold up a bit. Could you explain why the query planner would show like bitmap heap scan and bitmap index scan?
Good question. Let me re-enable our bitmap scan equals on. I'm gonna drop index. So in order to delete an index, it's drop index, then the name of the index that you want to delete. And then the question was, if we have explain select id tweets from tweets where lang equals index like this. In here, it lists bitmap index scan and it lists the bitmap heap scan. The question is, why does it list both of those two things? The answer is that what the bitmap index scan does gets the list of all TIDs and sorts them. And the bitmap heap scan takes the sorted list of TIDs and then scans the heap for those particular TIDs. For an index scan, those two steps, it's still doing those two steps. It just puts them all into a single step, and there's no sorting of the TIDs for a. So if we redo this with Americ, it has the index scan. It still finds the TIDs from tweets and then looks in the heap for those TIDs. It doesn't break it out into two separate steps though. The reason the bitmap heap scan breaks it out into two separate steps is because one of the special features of the bitmap scan is that it lets us combine multiple queries together. So what I'm going to do next, XHD tweets, we have currently one index on Lang right here. I'm going to create another index, create index on tweets country, country code, like this. And now I'm going to adjust my my query like this. So where language equals index or country code equals France, like this. And spell it correctly. And so here what we can see is happening is there's a bitmap index scan on the language equals tweets on this particular index right here. This index only has the language inside of it. And so this gets all of the TIDs that correspond to having the English language. Then there's another totally separate bitmap index scan that corresponds to the country index, where the country code is French. And so this is going to get a totally separate set of tuple IDs right here. Both of these, there might be some overlap between these tuple IDs because you can have an English language tweet sent from France, but there's going to be a lot of non-overlap between these two lists of tuple IDs. And then these tuple IDs are going to be ORed together. These two lists will be ORed together, so generating a new list that contains everything from this list or this list, and then do the bitmap heap scan on those two lists. So the bitmap heap scan, or the bitmap scan, which is shorthand for a combination of the bitmap index scan and the bitmap heap scan. One of the advantages of this that the other scan types don't allow is you can take advantage of multiple indexes. And you can't do that with any of the other scan types. But that's the, so to answer, this goes back to the question about why is bitmap index scan like separated out from bitmap heap scan in the query plan. And this is the reason, because we could have the bitmap index scan on multiple different indexes, on multiple different conditions, and then we can OR them together or AND them together and to create a new list and do the heap scan on that. Did that answer your question, Julie? Any other questions about the bitmap scans? So here, let's see, I want to rerun this query a couple of different times, a couple of different scenarios. And actually, let's go ahead and make this an explain analyze command. And so with the explain analyze, one of the things in the bitmap heap scan that it's going to give us is it's going to give us the total number of heap blocks actually accessed. So as it's doing its for loop in this bitmap heap scan, it's just going to count how many heap blocks it actually accesses. And so here it accesses 4,900 different heap blocks. And again, we had roughly 5,000 heap blocks. So this is, it's doing a little bit of filtering here, but it's not doing a lot of filtering. And that makes sense because English, there's just a lot of English language tweets. And so most heap blocks are going to have English language tweets inside of them. If I change this to get rid of the country code right here and only do English, we can see that we still get 4905 as our heap blocks. And so adding this extra condition on or the country equals France doesn't change the number of heap blocks that's going to be accessed. If we look at the execution time between these two conditions, so this here is with, again, only on English, no looking at France, 20 milliseconds. Looking at English or France, 22 milliseconds. So that extra 2 milliseconds is due to the additional computation processing here. Yes, we are accessing some index heap pages here, but in the heap itself, we're not accessing any additional pages. So very, very similar runtime right here. If we change this from an or condition though to an and condition like this, so where the language equals English and the country code equals French, most English language tweets are not sent from France. They're sent from English-speaking countries. And so when I run this, we can see that the execution time has gone down dramatically from 20 milliseconds down to 2 milliseconds. And we can explain that by looking at the total number of heap blocks actually accessed. That now it's only 100 heap blocks that are being accessed. So like, I don't know, 1%-ish, less than 1% of the heap blocks are being accessed. And the reason is in our bitmap index scan of our language, this gives us this, these two things give us the same information right here that we had before, but now we're looking for the bitmap and of those two lists of tuple IDs instead of the or. And so that greatly reduces the total number of tuple IDs that we're actually looking for. And so the total number of blocks also greatly reduced. In this case, the total number of heap blocks looked at, 106. And then if we look at the total number of rows actually returned, 109. So the vast majority of rows are in their own unique heap block. There's only 3 heap blocks that have duplicate rows inside of them. The other interesting queries, let's change this to our country code. Let's do or and say the country code equals US like this, explain, analyze that, hit enter. And now we can see that the sequential scan is, or the chosen algorithm that it's going to use is a sequential scan. We could use the bitmap index scan. I'm going to force our query planner for a second to use the bitmap index scan by saying set enable underscore seek scan equals off like this. So now, previously this command was using a sequential scan. I've just disabled sequential scan, so that's not allowed anymore. Now when I rerun this command, it will use the bitmap index scan. But up here you can see that the heap blocks is very, very large. Postgres is predicting that it's going to access 60,000 different rows. And so because that's such a significant fraction of the table, it thought that it would be better just to use a sequential scan and just access all of that stuff in the table directly without the overhead of visiting all of the indexes beforehand. If we change that condition from an or to an and conditions in general more restrictive than or conditions, and now we can see that it is back to using a bitmap index scan and a bitmap heap scan. In this case, the bitmap index scan is going to filter only on the country, only on US, and then during the heap scan, it's going to check all of those individual rows to make sure, right here it says recheck condition, to make sure that they pass the language check. Sorry, the filter right here is where it passes the language check. And so it could have put the, done 2 bitmap index scans and anded them together, but it thinks it's going to be faster just to do a single bitmap index scan and then filter them out like in a sequential scan on the bitmap heap scan right here. In general, the more restrictive these conditions are. So like if we change English again to Amharic like this, the more likely it is to use a more restrictive type of scanning method. Here, because Postgres is so confident that this Amharic language is such a good filter, it's not even going to bother looking at the country code at all, and just use an index scan directly on Amharic. Index condition Amharic, and not even bother with the country filter. So again, the takeaway of all of this is that there are many, many different combinations of ways that these indexes can be combined together in order to make your algorithms faster in different ways. And Postgres does a pretty good job of selecting which one is going to be the best for you, as long as you have provided it with adequate indexes. And so the trick to getting fast runtimes is provide Postgres with good indexes. Any questions about that? Okay. So that's these the table scanning strategies, and get my writing pad plugged in here so that we can start talking about the first of these integrated questions over here. Here's my cursor. There it is. There we go. So the first of these questions, well, let's see. All of these questions are related to a simplified version of our Twitter database with a user's tweets and tweets mentions table. The only difference between this database and the one that is in your PG normalized, so this is the same as PG normalized. The only difference is that there are just fewer columns over here just to make it easier to keep track of what's going on. This first problem right here is asking us what are the create index commands that are implicitly run by these commands up here. And this will be important for us when we're answering the following follow-on questions about how those indexes are going to be used. So in order to answer that, there's, well, at least in this situation up here, the only things in here that's creating indexes are the primary keys. Recall that primary key is unique and not null, and every unique constraint has an index associated with it. The reason that the unique constraint has an index is because when we're doing those select queries that we talked about in the locking section, those select queries, in order to make them fast, in order to make them run in logarithmic time, we want them to have an index that they can use. And so the unique constraint has to have an associated index. The syntax for creating an index that corresponds to a unique constraint. So let's say up here we wanted a unique index on tweets. We would say create unique index on tweets underscore id tweets like this. This is the same exact syntax that we've seen before. We just added this word unique right here, and that would make a unique constraint on this particular this particular column. So every time you see the primary key, you create a unique index associated with that key. So it'll be create unique index on, and then up here, users, ID, users, like that. For this one, no other indexes on the users table. Down here in the tweets table, we have a primary key right here. The references, references do not create any indexes. So we'll have another create unique index on this tweets. And then id underscore tweets, like that. And then for the tweet mentions, here we have a primary key that has 2 columns inside of it. And so that'll be on tweet mentions. I'll put it on a new line down here. Id tweets, comma, id underscore users, like that. And so there's only 3 indexes that are created on these 3 tables up here. Are there any questions about how I got those 3 indexes being created? Okay, so on your final exam, when you have questions like this, it's going to start with asking you what are the indexes that come with a particular problem. And if you don't get these indexes correct, you can't get the subsequent problems correct. So it's very, very important that you make sure you get this problem correct, that you understand what indexes get created by default. The second problem. So now we have some particular query, and it's asking list all the scan methods that could possibly used for that particular query. So here, the information that is contained in this query is id user, and we're going from the tweets table. So we need to look at our indexes, look at the tweets table right here, and we see that there is no index in the tweets table that mentions id users, and so there's no index that we can possibly use on this query. There is an index on the id users column in the users table, but because that's a different table, we can't use it. So the only thing that can be available here online on problem 2 is the sequential scan. Nothing else is available. And anytime you have a question that's asking to list what are the scan methods available, sequential scan is always available, so that's something that should always be put down no matter what the indexes are. Problem number 3, here we have on the users table, id users, and this is, we have that corresponding index right here, id users. This particular query, though, is also asking for a username, so we cannot use an index-only scan because this information right here is not contained in the index. So we can use a sequential scan, an index scan, or the bitmap index scan. But in particular, not an index-only scan. Are there any questions about either of those 2 problems? What what is available. See, one thing that sometimes, question?
Oh, yes, sir. So I just want to make sure that I understand this. So the reason that we cannot use index only and because we are searching for the column, so then which definitely right.
Exactly. So the question is why can we not use an index only scan here? And the answer is because we need to get the information username in order to do our result. And username is not contained in the index. Only the id users is contained in the index. And so that's why we can't use an index only scan.
So then if instead when we create the index on the user table, we do like create index on user and then ID user and then username, in that case then we can do it.
And then, yeah, so the question is, what if we also had a different create index command that looked something like create index on users of id users, comma username. In this case, that would allow us to use an index only scan. Yeah, good question. Any other questions about these problems? Maybe an important thing to keep in mind here is that I'm never going to ask you like actually which scan will be used, because there's like complicated algorithms that go under the hood in Postgres about that. So these are just like when Postgres is deciding which algorithm to actually use, what are the things that it might possibly be able to choose from? What are the things that it's physically possible to do these algorithms with? Okay, problem number 4 down here. This problem is related to the multi-column indexes. And some subtleties of multi-column indexes. So here, when I do select id tweets from tweets mentions where id users equals this, it's possible to use an index only scan. The reason is because we have an index that contains both id users and id tweets on the tweets mentions table. Scroll up just a little bit. Here, this primary key is on id tweets and id users, id tweets and id users. So we have all of the information inside of this table. The problem is the information is in the wrong order to be actually efficient for this query. We'll see, I'll write that out and then we'll see why that's the case. So our the order that our information is first id tweets and then id users. And so right here, I'm going to draw a little B tree looking thing similar to what we've drawn before. I'll just have 2 different entries inside of it. And the first thing that we're going to have in each of these tuples will be our id tweets, and then the id users. Apologize, that very that says id users right here. And so, for example, we might have like 99, and then id users here say be 55, and then over here our id tweets will be must be bigger 101. We're ordering from left to right. So the id tweets must be bigger, but the id users doesn't necessarily have to be bigger. Over here we'll have, so there's a 55. Over here we'll just have the number 3. And then all of our branches down here again, we're ordering first off of id tweets and then off of id users. So here, everything over here has to be less than 99 for id tweets. So maybe the number 5, but it doesn't matter how it's related to this id users. So we'll have 5 and then 7, something less than 35. The only time that the ordering between id users matters is when we have a match on id tweets. So if this is also 5 over here, so same id tweets number, then the id users number must be bigger than this 7. That the id users is only used to break the ties on id tweets. So 5, 9, like that. Then over here we might have, say, 100, 10, and then 101, 3, and so again, this has to be less than or equal to this up here. And then over here, maybe another 101, 4, and a 101, 5. And so if I'm doing a search on id users, I can't use really this, this table or this B tree at all to help me understand or help me filter off information about id users unless I'm also doing a search on id tweets. If I'm looking for all of the user ID number 5, for example, if I have this information up here, I don't know which branch I have to go down to find the user ID number 5. Maybe it's this one over here, maybe it's this one over here, maybe it's this one over here. It could be down any of these different branches. In this case, we happen to have user ID 5 over here. But there's no reason that this 7 couldn't also have been a 5. So the order is key in a multi-column index. And in particular, when you have a multi-column index, you want the conditions, the most strict filtering conditions, the most selective conditions, ordered left to right. So here, what we would want for this index, an index that would make this faster, would be create index on tweets underscore mentions, and then the order being id users first, because that's the one that's in my where clause that I'm doing the select on, and then id tweets second. And this will enable an index-only scan, actually using this filtering condition. Are there any questions about that? The references over here under the B tree page has a whole section, order of columns, and has a lot of pictures explaining how those the order of columns will affect the queries. And so if this is not crystal clear to you, strongly recommend reading this section right here, and that will hopefully clarify things, because the order of columns is something that's going to be hugely important on a lot of these problems. So this is a common way for students to miss points is to get the order of columns in the indexes incorrect. Questions about that? Okay. Then, so number 5, here, this question has some conditions that are not just equalities, but less thans or greater thans. And I want to pause to see how Postgres is able to do that efficiently with a B tree for all the different types of index scans. Coming back over to our references, here we go. So this is on the B tree page. There's a section, search by equality. It has this image representing a B tree. And you'll see that it looks very similar to the images that we had for a B tree. Some of the differences are that it starts with this meta page. In these pictures, each one of these blocks represents an actual page located on disk. And so there's one additional meta page that just stores meta information about the tree itself in Postgres. And then each one of these nodes represents both like the logical B tree node like we were drawing on the notes, and also a physical page in Postgres. And so you can see that in order to do a search, it's going to just do those like the binary search property going less than, greater than, finding which path to go down to find all of the particular corresponding nodes. And here it's looking for the key of 49, and so that's why it's finding 49 here. One of the things that I haven't drawn, though, in the drawings I've been doing on the notes are all of these arrows going from the left to the right on all of the nodes at the same level. And these are going to be important for the scans that are going by an inequality. Whenever you're doing a search for an inequality, one of the kind of really nice properties of a B tree is that it will give you all of the information back in a sorted order. So here, if we're looking for everything less than 35, then what we do is we first find where position 35 is. So here, following these this chain right here, we see that 35 should sit between 32 and 42. So this 32 is the thing that's less than 35. And then we have from each of these pages a link to all of the other corresponding pages on the same level. And so we can just do a for loop going along the bottom of this level like this to get all of these other all of these corresponding tuple IDs to all of these other matching tuples that match the query. This is for an inequality with just one condition inside of it. If we have a range, so 2 conditions, then it'll find either the top or the bottom one first, and then just scan until it hits the corresponding other side. So the still a very, very efficient operation. Get log in time to find the starting position, and then just O of k time, k being the number of entries that it's going to return, to find the ending position over here. This is going to be, well, yeah. So it's important for this sort of query like this. And so what this problem is asking, create an index so that the following query can use an index-only scan. Here we have two columns that we need to have access to, the id user and the created at column. We'll want to have the id user column first so that it can find the exact equality on id user, and then do the range on the created at. Again, the principle is whatever is the most restrictive condition should happen first, and then the least restrictive conditions happening second. So this one right here should be create index on tweets And then the most restricted first, id users, and then the created at next. You should work out for yourself. So make sure you understand why it would be bad to have it in the opposite order. Any questions about these multi-column indexes? Okay, so then this is our discussion of table scanning strategies. That's all of this stuff here. And next we'll go on to sorting strategies. And I think we'll be able to finish this today. So sorting strategies, basically anytime you have an order by clause that you're adding to your SQL query, you'll need to sort things somehow. And so that's the main situation where we'll need things to be sorted. There's two basic strategies for sorting, an explicit sort and an index sort, which we'll see later. The explicit sort has three different types inside of it. You don't need to know these three different types in detail. The main thing is to know that there's just an explicit sort, and Postgres will select for you automatically among these three different types. Those three different types are the top in heap sort, if you have a limit clause as well, and this runtime is O of in plus big in log in. The little n over here is the total number of rows in the table. The big N is the n in the limit. If you don't have a limit clause, it'll use quicksort for O of in log in. And then if things don't fit into memory, it will use a specialized merge sort algorithm that stores intermediate steps to the hard drive. So there's a lot of like really complicated, fancy code going on up here, and lots of like really good programmers have spent a lot of time on this code, and so sorting is about as efficient as it can be in Postgres right now. But still, sorting is like super, super slow. And anytime you see sorting happening in your query plan, it's something that you, if you can take that out of your query plan somehow, you'll get huge, huge performance speedups. So how do you take it out of the query plan? Using an index. So if we saw like this, whenever you're scanning an index, the tuple IDs that you get back are going to be returned in a sorted order. And so if you can take advantage of those being returned in a sorted order, then you'll get really, really good speed up in your queries. So let's come back over here and see what that can look like. So the query that we're going to work with, I want to select id users from tweets where language equals index, something like this. But now order by id users. Let's go ahead and start off with an explain right here. And so we've seen before, we've seen just this command right here without the order by, and we've seen that gives us the bitmap scan like this. With the order by, it's adding this sort node right here with the sort key on id users. In order to make this faster, one of the first things we should think about doing is making this an index only scan. So adding id users to the to our index. So create index on tweets, and then lang, comma, id users like this. And now that we've done that, explain that, we can see that not only does it go an index-only scan, converting the bitmap heap scan into an index-only scan, it's also going to get rid of the sort for us automatically because it's able to get the id user's results back in sorted order because they're already stored in sorted order on the table itself. If we don't add this order by clause right here, then yeah, still using the index only scan, and we'll still happen to get things back in sorted order. But the order by clause will guarantee that things get back in sorted order. Any questions about sorting in Postgres? So, where to go? So down here, getting more complicated queries. Create indexes, so the following query can use an index-only scan, avoid an explicit sort, and take advantage of the limit clause for faster processing. Let's also talk about how the limit clause interacts with all the things that we've seen so far. Limit is a little bit confusing because it interacts with basically everything in subtle ways. But with the things that we've seen so far, if you're using an index sort, then the limit will make it faster. If you're using an explicit sort, limit cannot make it faster. You still have to sort everything unless, sorry, I take that back. That the limit can still make it faster. It'll use the top in heap sort to make the limit faster. So sorting, limit will pretty much always make things faster. With our index scans, the bitmap